in this video, we will see what exactly is compressor surging and choking. So surging and choking are very important phenomena in the compressor. So it is very much important to understand what exactly is compressor choking and surging. So in order to understand this surging and choking, first let us understand what will be the compressor performance curve. See, this compressor choking and surging, it is not just applicable for just centrifugal compressor or just axial compressor. It is applicable for both centrifugal and axial compressor. Irrespective of the type of compressor, this surging and choking phenomenon is common. So on the y-axis, we have the pressure ratio, that is P2 by P1. It is unitless since it is a ratio. And on the x-axis, we have mass flow rate. It may be kg per second or meter cube per second, or whichever the unit, the flow rate which you require. So when we look into the performance curve of the compressor, we get a graph like this. This region, we'll call it a separate region. And let us consider a compressor. It may be, let us now consider a centrifugal compressor. So what happens in the centrifugal compressor? There are major components. First one is the impeller and diffuser. So these two are the major parts of the centrifugal compressor. Okay. So what happens is impeller also increases the pressure and diffuser also increases the pressure. So say now I am starting the compressor. Say now my starting point of the compressor is say A, this point. Okay, I have just begun to turn on. This is the inlet of the compressor, and this is the delivery of the, just after the diffuser is the delivery of the compressor. And say I am having a valve over here, and this is the downstream of the compressor. Say initially I am keeping it 100% close. 100% close. That is at point A. I am operating at point A. So what happens is when the delivery valve, this valve is closed 100%, what happens is the pressure increases only due to the impeller. Okay. So there will be, the diffuser doesn't contribute its quota to increase the pressure ratio. Only due to the churning action of the impeller, the energy of the kinetic energy of the impeller is imparted to the gas to raise the pressure. So that is why we can see the starting point is this one. Then the mass flow rate will be 0 because it is 100% closed, as I have closed this delivery valve. Okay, so slowly when I start to open, I can see that there is a increase in the pressure ratio. Initially, this is the positive slope of the graph. So why initially I can see an increase in the pressure ratio? Because the diffuser also contributes its quota to increase in the pressure ratio. It may not be having any rotating part, but due to the change in the cross-section area of the diffuser, it contributes its quota to increase in the pressure by altering the gas velocity. Okay, so initially the pressure increases, and there comes a point where I can reach only to a maximum pressure ratio, after which the increasing the mass flow rate doesn't increase the pressure ratio. So this region A to B, okay, is very unstable. I will talk about this. That is why we use the term surging over there. This region is stable, okay, and I'll be having a two different offsets from this same maximum pressure ratio, which is the best operating point. That is the best this point B is the where I can get the maximum pressure ratio, is the best efficiency point. So point B, I can say it has the best efficiency point. The offset from this best efficiency point, and from towards the left and the right, I can call it as the operating best operating point. So that is the region which usually the compressor is operating. Okay, say now I have from this 100% closed the delivery valve to I am opening, and I reach a point B. Say it is 60% open. I'm not fully opened it. I'm just keeping it at 60% open. If I keep it as say at 60%, I'm getting the maximum efficiency. Okay, and say I'm reaching this point, say C. Okay, just before the operating point. Okay, so what happens is when this is the delivery outlet of the compressor, just after the diffuser. So when I decrease the mass flow rate by creating the disturbances by you closing the valve, delivery valve, what happens is there will be a sudden gradual drop in the pressure at the delivery of the compressor. Whereas the downstream doesn't happen, the pressure is still higher. It doesn't fall rapidly, whereas this one, it rapidly falls. So what happens is the gas, it flows from high region to low region. That is from the higher pressure to low pressure. Okay, so further this reduce in pressure causes the and the gases flow from this delivery of the compressor towards the downstream, and due to the difference in the pressure, the net mass flow rate decreases. Again, the net mass flow rate decreases, and still and again will come and operate at a lower point, say D. Okay, so because the net mass flow rate decreases, because here say I am sending 2 kg per second, but due to the rapid decrease in the pressure at the delivery of the compressor, that is at the outlet of the diffuser, what happens is the reversal flow of the mass takes place. So again, the mass of the gas will flow from the downstream towards this one, because the always the gas or the fluid, any fluid, it flows from higher pressure to a lower pressure. Due to the difference in the pressure, it flows back. So what happens is when I sending it at 2 kgs, and but again I'm receiving it at 1, and the from the downstream I'll be getting to the diffuser at 1 kg per second. Okay, so what happens to the net mass flow rate? The net initially it was 2 kgs, but now it has been reduced to 1. So this cycle will continue. Okay, again and again. Okay, so this is called surging. Okay, so it is very dangerous phenomena. Okay, so now let us define. But after understanding this, now we have understood what exactly is the surging. So now let us define it. Okay, so it is the phenomenon, or we can call it as it is a disturbance that causes rapid drop in the pressure at the delivery of the compressor so which further causes reversal flow of gases. Okay, so this phenomena is called surging. Okay, and when I say this compressor graph to be like this, it is not exactly very steep. Okay, so it will not be exactly like this. We will get to see that it is slightly like this. Okay, so here I'll be having, so I can operate this region and this region. This is the operating point for me. Okay, so that is how it can be operated. And remember, surging is a very dangerous phenomenon. Okay, as it can lead to a catastrophic failure of the compressor, which may increase the downtime to repair, mean downtime to repair, and it may also increases the operating cost. It may significantly affect the bearing life. Okay, so what usually all the manufacturers do is, they will, when they design or manufacture a compressor, they usually have a set point below which the safety point, if the surging occurs beyond that point, the compressor shut down immediately. So many manufacturers use this auto surging uh, tool so that it is predefined so that it immediately shut down. So that is how this surging phenomena is prevented, and it is very unstable also. So once it reaches beyond that critical, that surging point, it starts to cascade its effects by decreasing the net mass flow rate, and again by decreasing the pressure. The cycle will continue again and again. So this the cycle, this pressure drop, this and the reversal mass flow rate happens. So due to which the surging occurs. So now, after understanding surging, now let us again draw a graph over here to understand what exactly is. Now choking we will understand. Okay. So choking is not a very dangerous phenomenon. So let me draw a realistic graph this time so that people will be able to understand. So this is the pressure ratio, that is P2 by P1. And as always, this graph starts at 1 unity because pressure ratio cannot be less than 1. You cannot, otherwise you are creating a vacuum. It cannot be the 1. So it will be like that. And on the x-axis, it is mass flow rate, that is meter cube per second or meter cube per kg. Okay, so what happens is, when we draw pump performance curve, we usually do it like this, and there may be a point after reaching a certain mass flow rate, you get a pressure ratio to be infinite, 1. Okay, that is the pressure ratio will be same. If you are supplying the intake of the compressor to be 1 bar, say if you are supplying 1 bar at the inlet, at the outlet also you will be getting 1 bar. If you're supplying 2 bar, outlet also will be getting 2 bar. So there may be a point when you extend that curve that it may or it may not be there. Okay. So it may or it may not be there. Remember that. It may, so it will not be there practically most of the time. Okay. So what happens is, now let me, so since this is the point A, it is operating at BEP, that is the best efficiency point, and say this is the choke point, sorry, the surging point, say let us say B. A is the best efficiency point, B is the surge point, and this is an irrealistic. And so after this best efficiency point, if I start to increase the mass flow rate, there will be a negative slope, which we can say that there will be a reduce in the pressure. So the pressure ratio gradually reduces. We can see that why, we'll understand why the pressure ratio decreases, and we'll get a point where beyond which we cannot operate. Okay, say let us say this is the point C, and this is the point where we cannot operate. Say this is called the point where we cannot operate beyond that point, is called choking. Okay, so compared to surging, choking is not a very dangerous phenomenon. And if you try to open the valve, say this is the point where I can get the mass flow rate to be maximum, say 2 kg per second, at when my delivery valve is at 80% open. Okay, so when I further open it to 100%, I will not be increasing the mass flow rate. The mass flow rate doesn't increase. Okay, we'll understand that why. So we all know that from the equation of continuity, okay, that is a discharge is there, that is we'll get the mass flow rate, say m dot, that is the mass flow rate equals velocity into area into rho. Since we are dealing with the gas, so rho comes into play. Okay, when we are increase, so what happens is when we are decreasing the, see, we'll write velocity equal to mass flow rate by area, and area is constant. We cannot change once the compressor is designed and manufactured and installed and commissioned. We cannot change the area, so it is constant. So what happens is when we increase the pressure, we are decreasing the density. That is the main objective of the compressor, right? We decrease the density so that we can pack huge volume of mass into a small space. That is what is the main motto. So we are increasing the pressure from P1 to P2 by decreasing the density. So when I decrease the density, what happens? The mass flow rate increases. Okay, so we are increasing the mass flow rate and also decreasing the density. So what happens is this tends to be very high. We can also reconsider this when we are increasing the mass flow rate. Like I said before, we are opening the valve, delivery valve, from 80% to 100%. We are trying to increase it from, say, 1.75 kg per second to 2 kg per second. And by increasing the mass flow rate, we are trying to increase the pressure, so the density decreases. What happens, since the area is constant, what happens, the mass flow rate we are increasing, and we get a velocity to be very high. So at a certain point, this point, what happens is the velocity may be, we may reach the sonic velocity, which the Mach number, for a Mach number to be 1, which means that the velocity of the gas will be equal to the velocity of the speed of the sound, or which means that the velocity of the gas will be equal to the velocity of the sound. Okay, basically Mach number is the ratio of the velocity of the gas to the ratio of the velocity of the sound. So when we say that Mach number is 1, it reaches a very high velocity, so which limits the amount of mass flow rate. Okay, beyond which we cannot limit. Even if we increase the area and we open the valve wide open, we cannot do it. We cannot increase the mass flow rate, and we cannot change the pressure. Okay, that limit, the compressor will not run. Even if you open the valve from 80% to 100%, the compressor will run entirely, no issues, but will reach a velocity of very high, which has to be considered, because when we increase the velocity, all the piping and the pressure vessels has to withstand that impact of that velocity. Okay, so it also, which is why it has to operate well below this C point, well below this choking point. So choking is a phenomenon where the speed or the velocity of the gas may reach the Mach number 1. Okay, so from conclusion we can see that when we draw a graph of the compressor performance, this is the pressure ratio, this is the mass flow rate. So when we draw a graph, okay, say this is the point B, and this is point A, and this is point C. So my best efficiency point will be between these regions, which is at offset of distance from point A. Okay, so many manufacturers, what they do is they always trying to prevent this surging by using auto surge shutdown. Okay, by integrating that. So we many manufacturers use it because it causes a huge catastrophic failure, and also huge running cost, operational cost, maintenance cost. So many manufacturers try to avoid that. So this is the typical graphs. This is for speed n1. Okay. So when I draw it for the n number of speeds, we get the curve to be like this. Say n1, n2, n3. So where n1 is greater, sorry, when n3 is greater than n2 is greater than n1. So I draw a point like this, and so this is the best efficiency point. Repeat. And this is the locus of all points for the surging. See, that is the point P, and this is the locus of all points join which have the choking. So it has to be operated well within this limit. Okay, and thank you for watching my video. Please do like and watch, and comment below for any suggestions. Thank you.